Hi, my name is Sydney Feldman, and this is a mini lecture about a scientific topic that I'm passionate about. When I first heard about this challenge, I was so overwhelmed. I love everything about science, math, physics, chemistry, biology. How could I possibly choose just one topic? It's like trying to pick your favorite child. So I thought about it a lot, and I decided to make a video about a quantum mechanics topic because, in my opinion, there's nothing more exciting than figuring out how the universe works and why it works that way. As I'm sure you've heard before, light behaves as both a wave and a particle. Now, in classical physics, there are clear distinctions between waves and particles. Certain equations describe waves, certain equations describe particles, and those equations cannot be set equal to each other. The Copenhagen Interpretation provides a method of thought that reconciles the behaviors of light as a particle and a wave and provides what is called a conception of wave-particle dualism. The Copenhagen Interpretation is not a definitive statement, but a set of principles. The first is that the mathematical wave function used to describe wave motion in classical physics is simply a probabilistic and theoretical description of the state of a system. It describes all of the possible positions, accelerations, and velocities of a single particle in that system. The next principle is the Heisenberg uncertainty principle, which states that there is a fundamental limit to the certainty of describing a particle's properties at a certain point in space. So let's say, for example, according to a wave function, one particle could be in 6 possible positions. Well, before the wave is observed by an experimenter or scientist, it can be thought of that the particle is in each of those 6 positions at the same time. Not just thought of, that's how the wave behaves, as if the particle is in all 6 of those positions at the same time. However, when the wave is observed by a scientist, it actually interacts with the laboratory equipment, and all of those 6 possibilities disappear, and it becomes one of the possibilities. This is considered a wave collapse, when all of the probable positions, accelerations, velocities of a particle or particles are eliminated and replaced with one actual position, velocity, or acceleration. From that point on, the system can no longer be described with the wave function. It switches from behaving as a wave to behaving as a particle. Another principle of the Copenhagen interpretation states that when quantum numbers are large, they represent properties almost identical to those of classical physics. However, when quantum numbers are extremely small, like on the atomic or subatomic levels, the results expected by classical physics and the results expected by the Copenhagen interpretation differ completely. Because of this, observing behaviors at atomic and subatomic levels is quite the paradox. By observing them, you drastically change the way they behave.